Good afternoon, students.
Good afternoon, sir.
Good afternoon, sir.
Okay, so any question, guys? So just to start with, so we have finished chapter 9. Okay, and by tonight or tomorrow, I will post homework number 4. Okay, and which will be due most likely by Friday or something. Okay. So please go through all the lecture videos. So videos number 31 to 34 are the course content. The actual, I mean, how to derive the strong form, then weak form, and then derivation of the stiffness matrix, force vector, and so on. And last 2 videos are solving the example problem. Okay, so we discussed the we actually discussed the problems which you have in the book itself. Okay, yeah. So 2D relationship problem as such involves like a lot of degree of freedom. So it is time taking to solve on paper, basically. Yeah. So on the other hand, the kind of like this 3-noded triangular element is easy. Okay, so we have taken such example in lecture 35. Okay, in lecture 36 we have solved one of the 4-noded elements problem, namely the rectangular problem, and also discussed ideas on how to use any quadrilateral element. Okay, general purpose quadrilateral element as well, using the isoparametric element. Okay, so whatever you learned in the heat transfer problem, you can apply here. Only thing is, problem is here little bit more complex. Okay, so instead of 1 degree of freedom per node, you have 2 degrees of freedom per node, and because of that you get complete little bit complex, but otherwise it remains the same. So any questions?
Hello, sir.
Yeah.
Sir, I have few doubts in the codes of chapter 5, sir. Scilab codes that you have sent.
Okay.
I have few doubts in that. Sir, like, sir.
No, okay. So first of all, the codes, all those things, we will not discuss here. Although I will listen to what you are asking. So these course is now out of codes. This is about learning the basics of finite element. Codes,
Yeah.
I assume you know programming, and the codes I sent you just for your understanding. Okay, it's just to help you. Okay.
Sir, I have doubts regarding the concepts of the.
Yeah. Okay. Okay. Go ahead.
Sir, in one of the problems for the solving a problem for the 3-noded element, we have taken written codes for writing the Gauss quadrature points. So if we take 2 Gauss quadrature points, then the values of xi1 and xi2 are -1 by root 3 and +1 by root 3. Okay, sir, but in the code there is an additional LE by 2 term also in the Gauss quadrature. So we don't have that term, sir, when we are doing it manually, like analytically when we solve it, we don't take that term of LE by 2.
What is LE there?
Length of the element, sir. LE is the length of the element.
Length of the element too. Okay, no, that is there actually. So what happens is you are actually the your integration. Okay, let me explain. Just hold on. So integration is basically for the whole length, right? And what you have learned. So just hold on. Okay, so basically what we are, let's say this is the one you want to integrate here, right? So this goes from 0 to x equal to 0 to x equal to LE, right? This is the thing, right? And you are going to integrate I equal to 0 to LE, and then you have a function, some function of x dx, right?
Yes, sir.
So this you have to convert into which form?
Into -1 to 1 integration we have to bring it.
Right,
Yeah.
yeah. So then you will automatically get there, this will be LE over 2, which is a Jacobian basically. Jacobian will come here, right? So this is Jacobian, sort of Jacobian, this -1 to 1, and f xi, and then
Desi.
dxi. So actually what you get here is j, right?
Hmm.
You get j, determinant of j, then dxi. The determinant of j is nothing but this guy.
Sir, this is there actually, sir. This also is there in the code, but
Okay.
separately when we are defining the value of xi, like xi1 and xi2. So
Acha.
instead of taking like xi1 equals to -1/√3, we are writing -1/√3 into LE by 2. Like sir, f of xi we are putting. So when we are going to put the value of xi, there also in the code it's there -1/√3 into LE by 2.
Okay, so maybe I'm not going through this one. I'm just using directly from here also. That you are saying, right? So actually, I'm
Mm.
not. Oh, okay, man. So just check. It may have some error. Okay, so I'm not saying
No,
that it not.
no, sir. If we don't add that LE by 2 term, then we cannot simplify that. That is correct, sir. Code is correct, but I can't understand the logic why we are using that.
Okay, so basically, I'm using the same thing. See, what happens is, so look at here. So if you want to integrate, let us say, and your function is like this, right? Your function is like this one. So we know that if you want to take just one point, say you want to just take this point, single point Gauss quadrature, then what will you do? You know
Then
that in that case, you just take the middle point, right? That's what you do.
yes, sir.
So what I will do in this case is I equal to, and this point is LE over 2, right? So I will just
Yes,
say I equal to LE over 2, right? And multiplied by LE. That's what I will do, right? The function at LE over 2, what I mean, right? So this is a function. This is fx. So what I did in the middle point, whatever the value is, I'm taking that, right? So, and I'm assuming same value from here to here, right? And multiplied by LE, this will give me the area, right? Yeah, got it.
yes, sir.
So average of this point, which will be here, and this multiplied by this length means this area. This area will be same as this area, right? So this is how we do. Similar thing is here. So either you can do like this one, or in case of this also you can do say. Let's say this is a linear case, right? Let's say you have fx which is quadratic. Yeah. So let's say your function is like this. Here from here to here, x equal to 0, x equal to LE, and your function goes like some quadratic function, right? Let's say this is fx now, or let's say call it gx to distinguish from the previous example. So if you have a gx, then what we do? So then we will take which value? We will take this value and this value, and right here, whatever which value is that? That will be simply -1 over √3, right? Corresponding to -1 over √3. This will be +1 by √3. But what of what?
Of the length.
So uh,
Of
no, not of length. You have to see if you had -1 to 1. then you had minus 1 over root 3, and here you had plus 1 over root 3. When you have 2, then it is like this. It means from middle, you are going this way, whatever the length of this is, multiplied by 1 over root 3, right? Is this, you are going from there. That means in this case, you have to first find out what is the value here. So what is the value here? Here it is LE over 2, right? Now, distance from here to here is LE over 2. So our Gauss point will be from here to here. What will be that value? That value will be LE minus LE over 2, LE over 2 minus LE over 2 multiplied by 1 over root 3. So this is the point where you will consider now. So this will be equal to LE over 2, 1 minus 1 over root 3. This is the point you will consider in that case, right? Similarly, here it will be 1 plus root 3 LE over 2. If you had this point at 0 itself, if you define this as such that in the middle this is 0 and here it is minus LE over 2, this is plus LE over 2, then you can remove this one, right? So your reference changes in that case. Got it? So what I mean to say is, if you had like this, if you had 0 here, here you had LE over 2, here plus LE over 2, then the Gauss point, you can simply, it says, you can say the Gauss point will be LE over 2, 1 over root 3.
Yes, I got it, sir.
Second will be LE over 2, 1 over root 3. So,
Yes, sir.
and you find out what is the value of the function here, and then you do. So you can also do like that. It is the same thing.
So this means that when the length of the element is not 2, it is just generalized case that we have written. If the length of the element is 2, then it will be 1. Then we have only 1 by root 3 and
Sure.
minus 1 by root 3.
Sure.
Okay, sir. Okay,
So
sir, I got it.
if the length is 2, it becomes automatically 2 over 2. That cancels out, becomes 1, right? Then you have just this. Yeah.
Okay, sir. Got it, sir. Got it.
Okay. Any other question? Any other question, guys? Yeah. Yes, Mohit?
Sir, it is accidentally touched.
Yeah, okay. Fine. So okay, so while you are thinking about the questions, okay, so I will like come back to the one question that was asked last time, and it is about the, like, if you have a quadrilateral element, let us say something like this, yeah, and you have x to y, yeah, and you may need that something will be needed at some xy. And since we have isoparametric element, and that means we have this xi and eta system. So how to identify what is the corresponding xi and eta? So it may be xi eta here. So we don't know how to do it. Okay. Okay. So basically this is there are many ways I thought of, like, but all are basically complex only. It's not that easy, basically. The one I suggested last time, it has, you have to solve the quadratic equation to solve it. One of the way also can be thought, that I think is the simplest one, is since this is anyway, this is bilinear, what we see that the x and y, so for example, the if you see like x is a function of, right? So n equal I, we write like this, right? Y I equal to 1 to I equal to 1 to 4, and then you have ni x, not xy but xi eta. So xi eta, and then you have x I, right? You have like this, and then you have also like this one. So I equal to 1 to 4 Ni xi eta and yi. So you already have that, and since Ni is has something like this one, right? So how is Ni xi eta has something like this is a function of xi and function of eta multiplied, where these are linear functions, right? These are linear functions. So basically what we get, this one is we'll have terms, constant term, xi terms, eta terms, and xi eta terms, meaning that same thing we can write something like this one, where xi is included inside that, right? So we can write x equal to simply x equal to alpha 1 plus beta 1 xi plus gamma 1 eta plus delta xi eta, right? 1 1. Similarly, y you can write it as alpha 2 plus beta 2 xi plus gamma 2 eta plus delta 2 xi eta. So this will be of this form only, right? So where x will depend on xi and eta, and the function there will be constant term, then xi term, eta term, xi times eta term. Why? Because this is how Ni has either constant term or xi term or eta term or xi eta term. So hence, because of that, directly from this definition, it's implied that this x and y will be of this. Now, next thing is just we have to actually find out the like alpha 1 and this alpha beta 1 on this type you have to find out, right? And how we can do, like we know that the first point, like x1, if we say x1, then this becomes the value alpha 1 plus beta 1. What is xi at x1? Xi is minus 1, right? Plus gamma 1. What is beta at x1? Is minus 1 here too. Plus delta 1, and this minus 1 multiplied minus 1. This is just simply 1, right? And so on. So basically what we will get something like this: x1, x2, x3, x4 will be equal to something like this. We will have alpha 1. So just write like this one. So we have alpha 1, beta 1, gamma 1, delta 1. And here you have the values. So you have 1. So alpha 1 here, so 1. So in all cases it will be 1, 1, 1. Then alpha 1 multiplies to xi value. Sorry, beta 1 multiplies to xi value. So xi value corresponding to each of these nodes. So what do we get? Here we will get minus 1. Then you get minus 1 again. Minus 1 multiplied minus 1, that becomes 1. Second case, xi is 1, eta is still minus 1, and hence the product will be minus 1. The third point, this one we have both positive and hence here positive. The third one we have xi minus 1, eta is 1. Okay, multiplication is like this one. So this is what the equation is, right? So now if you know x1, x2, x3, x4, you can find out this value. So basically we can find out alpha 1, beta 1, gamma 1, delta 1 is equal to inverse. You have to invert it. Yeah, so we have 1, 1, then minus 1, minus 1, 1, 1, 1, minus 1, minus 1, 1, 1, 1, 1, then 1, and then minus 1, 1, minus 1, right? And inverse of that. And then here we get x1, x2, x3, x4. So we got this value, right? Yeah. So basically here the now next we have to find out the xi value, right? So the getting the xi value, we will okay, just a minute, guys. Okay, guys. I think we are getting in the same situation. What I meant is not exactly this one. We have to write this xi at x1 and this. Okay. So okay, well, let me. So we made some mistake again. So what I meant is, let me write it again. So we have to write not like this one, but the other way around. So this we know already, and hence, so what I meant is, okay, not this. So let me cut it like this. Okay, so there's a mistake. So we'll not write like this. So we have like, we know this one, but we are not going to write like this one. So I'm going to cut it like this. Okay. We have to write other way around, meaning that we have to write like xi equal to alpha 1 plus beta 1 x plus beta 2. So not beta 2, but gamma 1 y plus delta 1 is xy. We write like this. Okay. Why it will be true like this one? Because we have in the both, this is bilinear, right? So this is bilinear, meaning that we have n1, the relationship between the two. If we see that in one side, so we have like we are scaling from here to here, and how we are doing? We are multiplying two functions like this one, right? So that means when we are writing ni like nixy, in that case also this will be retained. So there will be some other function. So let's call this f1 and f2. Similarly, it will be z1 x, right? z1 x times z1 z2 y, something like that. Yeah. Hence, this will be from we will have xy term there. So there will be x term, y term, and xy term. So this is basically what we are saying here is we can assume like this one, and then this also alpha 2 plus beta 2 x plus gamma 2 y plus delta 2 xy. This also comes like this one. So like if we can say like transformation, right? So our transformation original was from going from here to here. So this is x to y, and we are going from here to here like this. Yeah, and for that we use that. Similarly, what we are assuming, we are going from here to here to here, and we have the like this one, and we are assuming the similar kind of like a function. So basically we are going from here to here, and hence we can write like this. So x something like this. Ni xy will be equal to, right? And we write like that, right? So in fact, for this one, we can write like, and if we had to derive anything, any xy, like without using the isoparametric element, if we had to derive the stiffness, the shape function, then we could have written something like this one: nixy, then alpha 1 plus beta 1 x plus something like that, right? So alpha 1 plus beta 1x plus gamma 1y plus delta 1xy. So as such, our shape function will be something like this one only. Yeah. So instead of using this one, if we had to directly use this one, we would have used the Pascal triangle. Yeah. And from there we get 1 x y x y, and it would have been correct. Yeah. To begin with, it would have been correct. Okay. Okay. And that means we can also use the same methods as earlier. So we can say xi equal to summation of ni xi I, right? So where this I equal to 1 to 4, we can also write like this, where ni is a function of xy, right? So in this case, this is a function of xy. So I equal to 1 to 4 ni xy and xi I.
So
you can write like this one.
So
right?
it should be xi.
Not xi.
Sir, because the xi terms are known to. Okay, sir. No, okay. Yeah. Xi, sir, it's correct.
Xi I. Xi I is constant term, and x and y are the, it can
Unknown
take any
terms.
value, unknown
Yeah.
terms.
Yeah.
So what I mean to say is the same thing you can write like this one. Yeah. And hence you get ni believe something like this. My point is xi will be in term, since this has xy term, hence xi will have the term of this. So xi will be equal to alpha 1 plus beta 1 x plus gamma 1 y plus delta 1 xy. This is the, I'm trying to explain that this way also is true. If we have x here and you have xi eta and xi eta here, now inverse also true, where you can write xi here and you will have xy also. It is true, both way it is true. Okay, and hence now we can find out one-to-one correspondence. Yeah, so we can have now how we can do it. So we can have like C, we can write xi1, xi2, xi3. So let's write here. So when we have at the first point xi1 is -1, so we write -1. Second point we have xi equal to 1. Third point we have 1. Third point we have -1 again. So this is equal to, and again we will have x, y terms only. So we have here alpha 1, beta 1, gamma 1, delta 1. And here we will have those 1, x1, y1, x1, y1. 1, x2, y2, x2, y2. 1, x3, y3, x3, y3 together. 1, x4, y4, x4, y4. Let's call this one as matrix M. Okay. So what do we get? We will get simply this alpha 1, beta 1, gamma 1, delta 1 is equal to M inverse and this value -1, 1, 1, -1. Right? So, and similarly you can find out. Okay, so let's go to next page. So similarly, you can say eta equal to alpha 2 plus beta 2 x plus gamma 2 y plus delta 2 xy, right? And hence you will have the same matrix basically. So what you will get here, you will get alpha 2, beta 2, gamma 2, delta 2 is equal to M inverse, same matrix will be there because it will be x1, y1 and so on. And then you have xi at 1 is -1, at 2 is also -1, at 3 you have 1, eta, and then 4 is, so you will get this value here. So once you have these values, alpha's values, now you put x and y, and you will get eta, right? So that way, so basically, what we found out is, so let's call this one as a function of xy, xi as a function of xy, and this, let's call this is a g xy, and hence what we got is alpha, beta, gamma, delta we got already, and hence we know here that xi as a function of xy we got, and eta equal to function of another function g of xy. We got that also. Yeah. So this is a little bit complicated, but I think in computers can be done very easily. Yeah, but this, I could not find any simpler way. Okay, so this is the, I thought this is the most simplest one. Yeah. Any
Yes, sir, it's fine.
did you get it?
Yes, sir, understood.
Yeah. Okay. Any other question, guys? So programming related, any question, any comments, anything, we can discuss any kind of problem. So although the programs actually may have some errors, but you have to be careful. Yeah, so you have to check. Yeah. So I guess you have only 2 weeks remaining, probably, right? This week and next week. After that, we will have exam. Okay, so you have 6 lectures remaining. Okay, so lectures, actually I may finish in like 4 lectures or so on. Rest will be examples only. In last also I did the same thing. So there was example. Yeah. So next chapter is beam, basically, which will be different from what we have done so far. Yeah. Remember, a lot of material here is just to something that most of you have studied already. You know, so like a plane stress derivation. So all those things are not like it was not actually the finite element content, but still we derived so that you understand what you are doing. So from where it is coming. Yeah. Otherwise, content is not much. Yeah. So don't think that we have a lot of lecture content, a lot of this. Those are just revision. And especially that works for those coming from outside the mechanical engineering. For them, it works. Yeah. But most of you from mechanical engineering, that what I mean is those from mechanical engineering, those are just revisions. A lot of things coming from solid mechanics, coming from advanced solid mechanics. There's a derivation coming from mathematics also, like when you say divergence theorem. So we spend some time on what divergence theorem is. Even like traction, reading them, like finding out what is the what does the traction means. You know, so all those things are some revision. So that may be already somewhere. You know, so don't think that way. So the main content here is going from given a strong form, from there how we are going to the weak form, from weak form how we are going to the matrix system. This is the only thing. Yeah, and which is a simple path basically. So most of lot of time we have spent otherwise, like how to derive the strong form itself. So those things somebody may just say that this is an equation, you have to solve it. That's it. Yeah. So still we derived all those things so that before you solve the problem, you should know what you are solving. Yeah, so just to complete the picture. So otherwise, concept-wise, any problem, especially those coming from the mechanical engineering, is there any problem in understanding this mechanical problem to the elasticity problem and all? Okay, guys. So here I'm going to just talk about some shortcuts, basically. Yeah. So especially the finding out the some force vector. It is very intuitive here. Yeah. You don't have to use basically the integration to actually do it. Yeah. So let us say we have. I'm just going to have some examples, and let us say example is something like this. So this is a plate, 2D plate, and this is, so this one is a pin joint here, this is a roller joint, so this can move. And let us say there is nothing there, but you just have one force here. Then what will you do? What will be the force vector? Yeah. So force vector, let's say this, we are saying 1, this is 2, this is 3 and 4, and we want to make let's call this F0. This is the F0 which is hanging like this one. The force vector in that case, always it's good to draw the free body diagram. Okay, something you learned in your high school. Yeah. And what do you have? We don't know here, so you say this is R1, this is R2. Okay, there will be no R2 basically here. Yeah, so because of this, but say doesn't matter. So this, you have R2 here. Then here this will be R3, and here you have F0 and then nothing else. So you have to number, right? So what we see is degree of freedom number. You can see 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. And accordingly, we can write the force will be simply, if there is no traction given, only we have concentrated load at a node, and that is the easiest one, right? So we can just write F equal to, yeah, so F, so this force vector is equal to, and what it will be? Will be simply, we start here like this is 1, 2. So in this direction we have R2. So we write R2. Then next is R1 upward. So this is R1. Then is R3 upward. No, in this direction now. Third one, right? This one, so 0. So we have 0. Then we have upward R3. Okay. Then we have number 5, 0. Okay. Then we have number 6. So let's write number 6 right here. So 0. Then after that, 6 is F1, but downward. So we have to write minus F0. Yeah. And then 7, 8 is nothing. So 0, 0. So we write 0 and 0. So basically we go like this one. So sorry, because of the space, I'm writing like this one, but this is should go in one line. So it should be a column. So it's going like this one. Yeah. So notice that it's so easy to form this is the force vector. This is the, you can do it like that. You can make it more complicated now, right? So you can have a, let us say, instead of having this one, you can also have like let us say that same thing we have like this. So this could be like civil engineering problem, something like, say, and here you have it like a water here, like something like this, right? So you have here this could be something like this. Yeah. So different problem we are talking about, hence we have different setup. So we have like this one. Yeah. Okay. Now if that is a thing, there will be a water pressure here because of that. Yeah. So let's say that this is still here only, right? So it's still here only, right? But this is a structure, some structure where water is here, because of that there will be a loading. Yeah, so loading will be triangular. It will be something like this, right? So basically, what I mean to say is in this case, there will be a pressure which is acting on this one, and hence, if you draw it, so our forces will look like this. So like this. Okay. So how do you get here? Here we get something like this. So force will go like this one. So we have like this. Something like this one. Yeah. Pressure will be, say, it depends on the height, basically x. So from here, let's say this is what the measure. From here it is h, like this one, and the pressure P is equal to rho gh, right? Okay, some means it depends on h only. So h equal to 0, no pressure. H equal to more, it will be have more pressure like this one. Okay, then how to find out what will be the force in that case? That's the thing is, right? So here also we can say that there is a force here. Let us say like this one. So pivot diagram, if you see here, so what we'll get? We'll get a force upward. Let's call it R1. And what is the force this way? So there is no. So it's up to you how you number it. I said R1. Probably this would have been R1, but R1 equal to 0 in that case, right? So here there is no force this way. Why? Because this is a roller. It will not take force in this direction. So this is 0. So I will not do any write anything else. So R1 we have. Here we have both of them. So let's say this call it R2 and this call it R3. Done. And then we don't know what value we will get here and what value we will get here. Okay. Now, in order to find out, you know that in this case, 2/3 will come here and 1/3 will go there. So total force, if you find out, so total force on, so let's say A, B, C, D. So total force on CD or say FCD is equal to half multiplied by rho GH multiplied by so not rho GH, let's say it's called length CD. Okay, so LCD, let's call it LCD. Yeah, multiplied by LCD. So basically FCD will be equal to half rho Z L CD CD square. So this will be your total force, right? This is going to be total force. Okay, now 2/3 will come here and 1/3 will go here. So accordingly, what do we have? We have this force. This one is 2/3 here. So it will be 1/3 rho Z LCD square, and here it will be 1/3. So this will be 1/6 rho G LCD square will come here. Yeah. Now, if you have to write it, what is the value here and here, then we have to know the angle basically. So we have to. So first we have to find out angle. So whatever the angle is, let's say this is theta angle. Both will have theta angle, and accordingly we can find out the value of what? Force. So let's write in this case what will be the force? Force vector will be equal to. Okay, start with here. So we have the first degree of freedom starting from here. So we have 1, 2, 3, 4. Node number 1, 2, 3, 4. So we have this one 1. So we can also write this is 1, this is 2. Okay, then this is 3, this is 4, this is 5, this is 6, 7, and 8. 8 degree of freedom. Okay, accordingly we can write here the first one is 0, so write 0. Second one is R1, so write R1. We have to find out. Third one R2 and R3, so R2 and R3. Then here 5 we have to find out. Now 5, we know that at this point exactly we don't know, so we have to take the cos of that first of all, because this we know this is the final value, this is the final like magnitude, so we take cosine of that, so cos of that. And also notice that this is negative direction, because it says that our axis system is like this one, so positive is this way, this being negative, so we have to take minus sign as well and cos of this also. So that means you will have minus 1/3 rho g L C d square cos theta. So that's what we will get. And then this will be sine theta will be like this, but this will be downwards just because we have like this one, hence we have minus sign. If we had like this one, then no minus sign, then we would have plus sign. So like this now. So here we will write minus 1/3 rho g L C d square sine theta. Right? We get that. And similarly here is the same situation. Only thing is here is the magnitude is different. Otherwise, we'll have cos theta here also, because both are parallel. Yeah, so let's write next here. So we have this, and then minus 1/6 rho g L C d square, then cos theta, then minus 1/6 rho g L C d square sine theta and transpose of that. Yeah. So this is how you can, just looking at it, you can do it, right? So this is also coming from the basically the insight here is this is a structure, this is a force. Automatically the force there will be from the continuous system. From the continuous force, we have to divide into 2 nodes, and you know that here you can see the physics behind it, and the physics is if you have a load something like this one, and in that case the CG or the center of mass will be somewhere here like this one, that will be, and then it has to be supported here and here. So from here to here, this will be, yeah, if length from here to here is L, so this will be 2L/3, and this will be L/3. And if let us say total weight is W, then you know that reaction here will be W/3 will be the reaction here, and the reaction here will be 2W/3. And why? This is because of the you have to balance the moment. So moment about this point. So moment about this point. So what do you get? This is W/3 multiplied by 2L/3 has to be balanced by L/3 multiplied by 2W/3. So both will balance, and hence it's like that. Yeah. So this is the insight why it will work like that. Okay. So this is the insight basically we are getting, and you can write accordingly. Yeah. So force vector for simple examples, very easy. Similarly, let us say you have a triangular element, right? So I may ask, like one of the question may be that there is a force here. So there is a force in x direction here, like this, where this is F0, where at the center of mass, or this is the CG, you can say, or centroid, right? So this is centroid. So if there is a force which is acting at a centroid, then how to transfer from here to here? It's very easy. Okay, now, so let us say you have this being force like this one. Let us say the full problem will be something like this. Full problem is something like this, and then you have a like this. Yeah, so this is a problem, and only force given is this concentrated force which is applied here at the centroid. Then how to find out the force vector in this case? Again, it's very easy. From here we have to, since there is no node here, we node here only. So we node number 1, node 2, node number 3 only. Force is here. So how you can find out? Yeah, so since this is centroid, this will be just distributed 1/3 here, 1/3 here, 1/3 here, as simple as that. Yeah, and that means that we can write like this. So first we have the PY diagram, and we can have here R1, R2. So let's say here R2, this is R1, then this force R3, and then we have to distribute. Okay, distribute this one, right? So when you distribute that, then here it will be in whatever direction the force is, same direction this distributed force also be exactly the same direction. Here it is in x direction, so this will be also x direction. So we have F0 over 3, we have F0 over 3, we have F0 over 3 here, right? And hence we can write the force vector. Force vector is equal to, let's write here. So we get R1, then R2. So we get R1, but you have to add this also, right? So we have R1, but this also is there. So we write R1 plus F0 over 3, right? Okay. Then we have R2. So we have R2. Then we have this F0 over 3. So F0 over 3. Then we have R3. So we write R3. Then we have F0 over 3. So F0 over 3. Then we have 0. There is no force, other force here. So this will be 0. So this transpose. So we got all the forces here automatically. You will get 1/3 also, because the forces, as you know, like in order to get that, this you can assume as a body force, right? And you know that forces due to the body force is equal to like FBI is equal to what you do, NIB d omega. You do like this, right? So, and you know that the shape function has 1/3 value. All shape function will have same value at the centroid, because this centroid divides the circle into equal areas, right? This area, this area, this area. Okay, and hence you will get 1/3, and hence the value of this is basically 1/3 of since B0 will be equal to Ni value at the centroid, which is 1/3. So you will get 1/3 multiplied by F0. So automatically, mathematically also, you will get the same value, and hence you are getting like that. Yeah, fine.
Yes, sir.
Yeah. Okay, so this is the last example I'm taking, and again this is the insight only. So in a triangular or any triangular, or it could be quadrilateral, doesn't any no problem. So let's say now we have something like this one, right? Okay. Okay, this problem, and now the force is now in the middle here. Then you know that half will go here, half will go here. If that's not there, let's say your force is here, somewhere here, then what will happen? Yeah, so then in that case, let us say the total from here to here, from to here it's A, and from here to here is B. Yeah, and then the force here. So so how will it going to distribute it? So let's say this is going to be distributed something like this. Here, this again, this will be parallel only. This will be parallel to this only, same parallel only, but the value will be here. Let's say this value is P naught, which is given. So here the value will be P naught multiplied. Since this is closer to this point, B is smaller than A, this should get higher reaction, right? Higher force distribution, right? Okay, and hence this will be P naught times A over A plus B, because A is bigger than B, hence in proportional A will be here, and here this will get P naught B over A plus B. So you are distributing in a ratio of what? Ratio A and B. So this is A and B. So force wise, the distribution here will be proportional to A, and here it will be proportional to B. Yeah, so that the moment will be the same. Finally, this is about the moment, right? So so that the moment will be same. So the original was here, and which is from here to here is A, from here to here is B, and hence moment wise, you will see the moment because of this will be P naught B times A over A plus B, multiply some angle, right? Here also it will be P naught A over A plus B multiplied by B. So both terms you will see exactly the same. This will also become P naught AB. Here it will also become P naught AB, and hence those will be the same. So if you just apply some mechanics, right, like a basic, like all the forces has to match, all the moments have to match, that is has to be balanced, automatically you can see how the forces are distributed. Yeah, so this is again nothing new I'm telling. Don't think that makes it difficult. I'm making it easy. These things are already you have studied in your high school, in first engineering mechanics, in solid mechanics, like in other courses as well. So I'm just telling here so that you have more insight about how you construct the force vector. Yeah, so that is all. Yeah, any other question, any confusion in what we were discussing? Yeah, okay. If there is no question, guys, okay, thank you. See you next time. Okay, again, please start seeing the video lectures, latest one, 31 to 36, because I'm going to post the homework very soon, either by tonight, definitely by tomorrow. Okay, so please do that. Okay, and deadline will be Friday probably, so please do that. Okay, guys, thanks. See you later.
Thank you, sir.
Thank you, sir.
Thank you, sir.